Student friends, in yesterday's lecture, almost all we completed the fourth topic of your syllabus, and that is field effect transistor, in which topic we studied the meaning of FET, classification of FET, difference between FET and B.Sc-I. Then we have studied construction, working, and IV characteristics of N-channel junction FET. Then we have studied the parameters related with the FET and also the relation between them. After that, we have studied the depletion enhancement MOSFET, its construction, its operation, its IV characteristics. And at last, we studied enhancement metal oxide semiconductor field effect transistor, that is the E-MOSFET, its construction, operation, and also its IV characteristics. Friends, now there is a time to solve some numerical examples based on the formula which I asked to remember. These formulas are just I will revise, depending upon which we are going to solve the numerical example. The first formula to be remembered by you, and that is ID, that is drain current, is equal to IDSS, that is saturated drain current, into bracket 1 minus VGS upon VP, obviously bracket square. So this is the important formula which is to be remembered by you. Second formula to be remembered by you, and that is RDS is equal to delta VDS upon delta ID. That is a drain to source resistance. Third one is transconductors GFS or ZM, that's equal to delta ID upon delta VGS. And last one is amplification factor, which is the ratio of delta VDS upon delta VGS. You have to also remember one more formula, and that is relation between FET parameters, mu is equal to ZM into RD. These formula will help you to solve the numerical examples which are likely to be asked on the topic known as field effect transistor. Student friends, let me begin to solve some of the numerical examples. Let me begin with the first example. For FET, IDSS is 15 milliampere. It is given. VGS of it is given as a minus 5 volt. Find ID for VGS equal to 0 volt, comma minus 1 volt and minus 4 volt. Friends, this is a single example, but three calculations are essentially needed. Same quantities to be calculated for the different value of VGS. Here we are going to calculate the value of ID for different value of VGS for given IDSS is equal to 15 milliampere and VGS off is equal to minus 5 volt. The formula to be used is ID is equal to IDSS into bracket 1 minus VGS upon VP bracket raised to 2. So this is the formula to be used. Value of IDS is 50 milliampere. VG is equal to minus VGS of means VP. That is a pinch of voltage. And you have to calculate ID for VG is equal to 0 volt, minus 1 volt and minus 4 volt. First of all, we have to calculate the value of ID for VG is equal to say 0 volt. For VG is equal to 0 volt, ID equal to IDSS, it is 50 milliampere, that is 15 into 10 raised to minus 3 into bracket 1 minus VGS it is 0. For 0 volt we are calculating. VP it is minus 5 bracket square. 0 upon minus 5 it is 0, 1 minus 0 it is 1. Therefore it is 15 into 10 raised to minus 3 into 1 square, that is 15 into 10 raised to minus 3 ampere. So that comes to be 15 milliampere. This is the first calculation we have did, and that is for VG is equal to 0 volt, ID comes to be 15 milliampere. Now say for VG is equal to minus 1 volt. So for VG is equal to minus 1 volt, again use the same formula. ID is equal to 15 into 10 raised to minus 3 into bracket 1 minus 1 upon minus 5 bracket square. Which one can write it? Minus 1 upon minus 5 is plus 1 upon 5, 1 minus 1 upon 5. So that is 15 into 10 raised to minus 3 into bracket 1 minus 1 upon 5 bracket square. 1 upon 5 means 0.2. So that's why 15 into 10 raised to minus 3 into bracket 1 minus 0.2 bracket square. So that is 15 into 10 raised to minus 3 into 0.8 bracket square. 0.8 square is 0.64 into 15 into 10 raised to minus 3. That comes to be 9.6 milliampere. So for VG is equal to minus 1 volt, ID equal to 9.6 milliampere. What we are observing here, as VGS increases, ID goes on decreasing. Last value we have to calculate is for VG is equal to minus 4 volt. For VG is equal to minus 4 volt, use again same formula. ID is equal to 15 into 10 raised to minus 3 into bracket 1 minus 4 upon minus 5 brackets. It is 15 into 10 raised to 3 into bracket 1 minus 4 upon 5 bracket square. 15 into 10 raised to minus 3 into bracket 1 minus 0.8. 1 minus 0.8 means it is 0.2 square, 0.4, 0.4 into 15, that comes to be 6 milliampere. What is the effect we observe? For fixed value of IDSS and pinch of voltage fixed value, if you go on, change the VGS from positive to negative, drain current goes on decreases. This is because gate to source voltage is reverse biased, and when VGS increases negatively, channel width decreases, and that's why the drain current decreases. This is the effect one can observe, and one can solve the examples in this particular manner. These examples may be going to ask in the objective type questions also. Second example, for FET, IDS is equal to 12 milliampere, VGS of is minus 20 volt. Find ID for VG is equal to 0 volt, minus 5 volt and minus 10 volt. Friends, Same formula is there. Same calculations are to be done. Similar way we have to proceed. Only the values are going to change. So for VGS equal to 0 volt, IDSS is 12 milliampere, that is 12 into 10 is minus 3 into bracket 1 minus VGS is were considered to be at 0 volt upon minus 20, it is 0, that is 12 into 10 is to minus 3 into 1 square, that is equal to 12 into 10 is minus ampere, that comes to be 12 milliampere. Next one is for VGS equal to minus 5 volt, that is ID is equal to same formula IDSS, that is 12 into 10 is to minus 3 into bracket 1 minus VGS is minus 5 upon VGS of, that is VP is equal to minus 20. 5 upon 20 it is 1 upon 4. 1 upon 12 into 10 is to minus 3 into bracket 1 minus 1 upon 4. That comes to be 12 into 10 is to minus 3 into bracket 1 minus 0.25. That is 12 into 10 is to minus 3 into bracket 0.75 bracket square. Its square comes to 0.56. 0.56 into 12 into 10 is to minus 3, it is 6.75 milliampere. This is second calculation. Another calculation we have to do for VGS equal to minus 10 volt. So for VGS equal to minus 10 volt, again use the same formula. ID is equal to 12 into 10 is to minus 3 into bracket 1 minus 10 upon minus 20, that is 1 upon 2. So 12 into 10 is to minus 3 into bracket 1 minus 1 upon 2 bracket square. 1 upon 2 means 0.5. So 12 into 10 is to 3 into bracket 1 minus 0.5. 1 minus 0.5 it is a 0.5, so it's a square, it is 0.25. So 0.25 into 12 into 10 is to minus 3. That comes to be 3 milliampere. So this is how one can solve the examples. But every time the conversion from milliampere to ampere, don't forget it. It is already converted. It's 12 milliampere. We have converted 12 to minus 3. Next example. For FET, 10 volt reverse voltage is applied. So gate and source is reverse biased. For that VGS applied to be 10 volt. It is given. If gate current is 0.1 microampere, that means the input current, gate current is given. It is IC equal to 0.1 microampere. Calculate the input resistance of that. Read the example for FET 10 volt reverse voltage. Means VGS is given 10 volt. Gate current is given 0.1 microampere, 0.1 into 10 is to minus 6. You have to calculate input resistance Ri. Formula is Ri is VGS upon IZ. So the input voltage upon input current. So VGS is 10 volt upon 0.1 into 10 is to minus 6. 10 upon 0.1 means 100 into 10 is to minus 6. Oh. That is 10 to 6 ohm means 1 mega ohm. So 100 into 10 to 6 means 100 mega ohm. So this is the input resistance of the FET, provided input voltage and input current are given. Next example is in FET RD is equal to 10K, means drain resistance is given as a 10K. GM is given as a 5 millimoles. Calculate the amplification factor. Given quantity RD it is given 10K, GM is given 5 millimoles. Amplification factor means mu is to be calculated. The formula to be used is mu into GM into RD. So RD is 10 into 10 raised to 3. GM is 5 into 10 raised to minus 3 moles. 10 raised to minus 3, 10 raised to plus 3 cancels. 10 into 5, 50. So amplification factor is 50. Such a simple examples are asked in objective type questions. Alternatives are given. In that alternative, one of the alternative is 50. Next example is find GM if mu is equal to 80 and RD is equal to 400 kilo ohm. So here RD is given 400K, GM is to be calculated, mu is equal to 80. Same formula to be used, mu is equal to RD into GM. Mu is 80 is equal to 400 into 10 raised to 3 into GM. GM is equal to 80 upon 400 into 10 raised to 3. 80 upon 400 is 0.2, 10 raised to minus 3 moles. So that comes to be 0.2 millimoles. So that is the transconductance, how we have to calculate. Next one is forfeit. Mu is equal to 42, GM is equal to 3 moles, find RD. Here RD is to be calculated, GM is given 3 moles. Moles is the unit of transconductance. And mu is given an amplification factor that is 42. Formula again same, mu is equal to RD into GM. Therefore, RD is equal to mu upon GM. Mu is 42 upon 3, that comes to be 14 ohm. So its value comes to be 14 ohm. Next example, in JFET, change in VDS is 8 volt. To change in drain current 40 milliampere. To change the drain current of 40 milliampere, VDS to be changed to 8 volt. Then what is to be calculated? Calculate drain resistance. So change in drain current, delta ID it is given 40 milliampere. Delta VDS it is given as 8 volt. Drain resistance is to be calculated, RD is to be calculated. Here some different aspect is there. The formula used is drain resistance is equal to delta VDS upon delta ID. Delta VDS is 8 volt. Delta ID is 40 milliampere. So 40 into 10 raised to minus 3, that is ampere. Therefore 0.4 into 10 raised to 3 ohm. That comes to 200 ohm as a RD. So the simple examples are asked in the objective type questions. Next one is, in ZFET, VGS changes from 8 volt to 12 volt. To change the drain current from 10 milliampere to 6 milliampere, calculate the transconductors. So change in VGS is given, that is from 8 volt to 12 volt, and change in drain current is given from 10 milliampere to 6 milliampere. Therefore, given quantity delta VGS equal to change, that is 12 minus 8, that is 4 volt. Delta ID is from 10 minus 6, again it is 4 milliampere. You have to calculate ZM. Formula is ZM is equal to delta ID upon delta VGS. All this formula we have studied when we have studied a theoretical aspect of the FET. That is FET parameters. When we have studied, we have defined all the parameters along with the formula. And also we have studied the relation between FET parameters. So use the formula that ZM is equal to delta ID upon delta VGS. So delta ID, it is 4 milliampere upon 4 volt, that is 4 into 10 raised to minus 3 upon 4 volt, that is 1 into 10 raised to minus 3 moles, that comes to be 1 millimoles. So this is how the transconductance is to be calculated. Next example, this will be the last example. For given FET, VDS is 6 volt, VGS is 0.2 volt, find amplification factor. So given that delta VDS is 6 volt, delta VGS is 0.2 volt, mu is to be calculated. Formula to be used is mu is equal to delta VDS upon delta VGS. Delta VDS is 6 volt upon 0.2 volt, that comes to be 30. Friends, this is how the numerical examples on the topic field effect transistors are likely to be asked, and you have to solve accordingly. But don't forget the conversions, that is from milliampere to ampere, ampere to milliampere, ohm to kilo ohm to ohm. These conversions don't forget. If you forget this, even though your numerical value is same, it may create problem while searching answers in your objective type questions. So that's why do conversions wherever those are necessary. Friends, this is how you have to solve the numerical examples. There are many examples which are available in the books, in the notes even. Get it, solve it. If you are unable to solve, then try to contact me on my mail ID on WhatsApp group. Quote your example on WhatsApp group. I will solve you and I will send you. But try it yourself, solving the examples. Without solving examples, don't say that, sir, I don't know how to solve. Try it. If you are unable to solve, please contact me on my mobile number, on my mail ID, or even on the WhatsApp group. Student friends, that's all about the topic number 4, that is field effect transistor. Next time we'll go for the last topic of your syllabus, and that is known as thyristor. Again, it is a kind of a different topic related with study of some new semiconducting devices. Friends, today we'll stop. Next time we'll go for the new topic.